Greetings, this is Artie from Artifact Electronics. In this episode, we'll be looking at this useful little device that is called a dim bulb tester, or DBT for short. Now the name is a bit of a misnomer because it may lead people to believe that this is a bulb tester, but it isn't. It actually is a device that will detect shorts in devices that you plug into here, and if a short exists, it will indicate so by lighting up the bulb brightly to its full brightness actually, and the bulb will leach most of the power flowing through the circuit so that there's very little power left to go into the device with a short, thus preventing damage in that device. So whenever you have a new piece of equipment, you should not plug it directly into the wall, but rather plug it into this and then power it on, and it will tell you very quickly if there is a short while protecting the device. Now notice that this doesn't have a switch on it, and the reason for that is that essentially the switch on the device under test is what becomes your switch. When you plug this into the wall and there is no load plugged in, it's an open circuit and it won't really do anything. I mean, it is a live outlet, but there is no current flowing in this. And when you turn on the equipment, that is when a load starts appearing here. That's when this will start working and do its job. Of course, right off the bat, safety comes first. This is powered by your AC voltage, and even though when put together properly, your exposure is pretty much limited to plugging something in here and then unplugging it, but still be careful. There's a lot of voltage in here and it will bite. So how does this work? Well, this is basically a light bulb wired in series with this outlet. You have to use an incandescent bulb. CFLs and LEDs will not work. And the whole thing works on the principle of how a filament in this bulb reacts to power draw. Now we need to match the bulb wattage to the equipment under test. And a rule of thumb there is the bulb should be approximately rated at 150 to 200% of the power requirements of the equipment. Simply said, you have a device that is rated at 100 watts. You use a 150 to 200 watt light bulb and it'll work for you. The way it works is when the load is plugged in here, if the load is drawing excessive power, basically the light bulb will draw all the power it can and light up brightly, telling you that there's something wrong, while at the same time starving the load from power so that the load can't self-destruct or blow up or whatever. And that's the entire principle that this tester works on. And what is so good about it is it takes the filament about 100 milliseconds to heat up. So yes, it is not ideal, it will not instantaneously cut power, but there's only so much damage that can be done in 100 milliseconds, and that's what makes this really effective. The first thing you should do is have a good understanding of how bright this bulb gets when the load is at a dead short. And the easiest way to test that is I have a test plug here that has the blades shorted together, and when I plug it in, this thing should light up at max, and it does. It's drawing all the power it can get, and there is still power running through this. Of course, the circuit has to be complete, but it's very little. And even though this is hard to show pictorially, I had this running before for a while, and now it's been running, and if you touch this, or the plug, you cannot detect a rise in temperature. And that proves that essentially this is saying, you're not getting any power over here. I'm using it all up for myself. So how do we wire this? Well, very simply. This is the AC plug that goes to the wall. And the part of the plug that that is fat or has the protrusions on it, the polarizing part, is the neutral light, and that goes straight to the outlet. The slimmer plug goes through the light bulb and to the other side of the plug. And that's it. The only other thing in here is that you're planning on testing equipment that does employ a grounded plug. Then what needs to be done is your power cord will obviously have to be the grounded type. And what you do is you connect the ground from the power plug directly to the ground on the outlet. So-called cheater plug here. You should never defeat ground on equipment that requires it, and vice versa. You should never force ground into equipment that doesn't have it. A lot of people think that, this is old equipment and it doesn't have a ground plug, it's unsafe. Let me just give it a 3-prong plug and connect the ground to the chassis and the equipment. That can be lethal to the equipment as well as yourself, because there was no standard in the old days as to what potential the chassis sat at. It could be at ground, or it could be at one directly connected to one of the legs of the AC power coming in. So rule of thumb is don't play with the number of prongs on the power plug in your equipment. But if you wire this in, you could theoretically build this with a 3-prong plug, and it just wouldn't come into play when you plugged something in that didn't have a 3-prong plug. The ground does not affect operation of this in any way, shape, or form. So what do we need to build one of these? Well, first we need a base. I used a wooden base, some scrap wood I had, and the dimensions are dependent on the size of the parts that you're going to get. Now what we'll all need is a power plug, or a power plug and wire, and what I did was I just bought an inexpensive extension cord, non-grounded, and snipped off the female part. Now remember, we talked about if you are trying to use grounded equipment, then you better buy an extension cord that has a ground plug and wire it properly. The outlet itself, you will need, of course, an outlet, a mounting box for the outlet, as well as a cover plate. And if we look in here, remembering the schematic is that we have one of the legs of the AC wire coming in and going to one end of the load. Then we have a wire coming out of here going to the socket. And the way that works is removing the socket, which is another part you're going to need. If we look underneath, we will see that the other leg of the AC cord is tied directly to one of the contacts here, and the remaining contact is wired to the second side of the outlet. And that's pretty much it. The only other thing to note is that I had to use spacers to mount the lamp socket because the contacts and the wires kind of protrude from the bottom of it, and you can't mount that thing flush on this baseboard. But let your imagination run wild, and again, it's very simple to build, and you should be able to get all of these parts at your local hardware store. Well, time to go for a test drive. Our subject, or guinea pig, is going to be a Heathkit scope. It's a model O-12, circa 1957, and entirely tube-driven. Now, let me caution you, I'm not going to make any repair attempts on this in this episode, because I'd rather concentrate on the DBT and other methods for now, but if you stay tuned long term, I will devote an episode to checking this guy out and fixing him. But he is functional enough for us to do a test. So as I explained, the very first thing we need to do is, well, of course, plug in the device under test, which is the scope, into the outlet, plug the DBT into AC, and insert a bulb. Now, the largest wattage bulb I have is a 100-watt bulb, which is a little bit low. I mean, this thing is rated at 80 watts. Well, actually, for 80 watts, 150% of 80 watts is 120 watts. So, yes, we are low. But let's give it a try anyway. And if that doesn't work, figure out what to do next. So first we do our brightness test to get our eyes used to how bright this bulb's getting. And there's the bulb lit up at 100 watts because I just inserted a short. Now, and you're probably going to have to take my word for it because this bulb doesn't show up too well on video, but I promise I'll tell you the truth. But now it's time to turn on this guy. And the bulb slightly surged. You could see it glow, then it went off. But the tubes are still warming up. And as the tubes warm up, now it lights up again. And my best guess is it's probably at about 10 or 15% of max capacity on this. Let me briefly turn off the room lights so you can see for yourself. So it is leaching power, but the scope came up and it put a, well, that's interesting. Look at what happens to the trace when I touch it. Well, that is something that's going to have to be left for the actual repair video. But what, of course, this proved was the scope is not shorted, and as a matter of fact, this one actually comes up and puts a something that kind of looks like a trace or a dot up there, even though it also functions as a touch plate right now. And that's going to be interesting to look into. However, what we do want to do is get this to a point where the bulb doesn't light up at all. I mean, there's always going to be a little bit of power on the bulb because otherwise, you know, it has to complete the circuit. But we absolutely want to minimize that. So let's try to figure out what to do when this is the highest wattage single bulb I have available right now. And what we're going to do is another little device I built. Well, built is overstating it. Another little device I put together from off-the-shelf parts. And I think I'll call that the DBT Expander. And I'll show you what it does. Well, first let's take this bulb out. And remember I spoke about electrical safety. And I need to add to that, be aware and practice thermal safety too. Especially a 100-watt bulb gets very hot, even when it's only lit up partially. Now it's cooling down, but I can still feel it. So what we're going to do here is the expander, which looks just like a power strip, which is exactly what it is. What we're going to do here is, instead of using a single socket, we are going to use this socket. Now remember, it is plugged in, but it's off. There's no live circuit in here. And to do it correctly, I should unplug it, but I didn't. Use a little adapter and you plug in the power strip. And then you put a complement of light bulbs in there to make up the wattage that you're looking for. And I got a little socket to outlet converter here. So first I'm going to put in a 100-watt bulb, and then I'm going to put in a 40-watt bulb. and that basically make it look like there's a single 140 watt bulb in here. Of course, it's never that simple, but for the purposes of the test, it should work. So now what we should see is maybe they'll light up a little bit again, but once it reaches a quiescent state of operating, then these should be getting slightly warm to the touch, but they shouldn't light up, meaning that they're leaching a minimal amount of power from the whole thing. So now that we're ready for that, let's go ahead, turn it up. This is the intent, not just the power knob, but intensity too, and give it some time. We can see the dot appear on the screen, and it's gravitating towards the center. Now notice my hand is on here. I think I'm still changing the width of the dot. Yeah, I am. Gets a little narrower there. But looking at it, I can see, and again it's probably difficult to see on the video, but the 100 watt bulb is lit up a little bit. I can actually see the filament. And this one is also getting warmer. So actually both filaments are lit up, at a minimum of course. So let's go even larger. Let's remove the 40 watt bulb and put in a 100 watt bulb. Now that should give us a minimum of power leach on the bulbs and make the scope be able to fully power up. So staring at the bulbs again, I still can't see the filament light up. Wait for the dot to gravitate towards the center, which seems to be what it tries or wants to do. Let's see if my hand still has an effect on it. And it does. I cannot see any lit filaments in the bulb. They are slightly warm. And again, that's to be expected because current has to flow in order to complete the circuit, but they're not lit up at all. And I'm assuming that the scope is getting full power right now. So it works. It told us that there is no short. And it kind of disproved the put in a bulb that's 150 to 200% of the rating in there. I went higher. I went to what, 200, I went to 250% of the rating with a 200, well, with 200 watt bulbs, i.e. a 200 watt bulb, and that seems to work. So one last thing to do is to take the DBT out of the circuit and plug this guy in directly into the wall and see what happens to the display then. How much do these bulbs falsify operation of this device? So I unplugged the scope from here, plugged it directly into the wall. One other thing to be aware of is on tube-powered equipment, you shouldn't power cycle devices like this quickly. I.e., don't turn the power off and turn it on immediately again. It may result in a blown fuse because the tubes are hot and you need to give, it's almost like a computer where you want to let the reset capacitors for the processors discharge. I generally turn it off, wait for a little while, and then turn it on instead of rapidly turning on and off. So now the DBT is completely out of circuit, and now we can turn on this guy and see how similar the dot on the display is going to be as compared to when we had the 200 watt bulb load, let's call it. And we can see it's still a little bit different. It is wider than it was before. And the interesting thing would be what happens if I put my hand on it now. And I don't know if you can see that, but it's actually getting slightly wider when I touch it now. So there is interaction with the DBT, and to do proper tests of repairs you've made, or if you're just testing testing component values or whatever, be aware that the DBT will cause, I shouldn't call it aberrant behavior, but the behavior will be different when it's powered off the DBT, even with the large bulbs, as compared to being plugged directly into the wall. I mentioned that I'd show you an alternative to the DBT, and that's this guy. This instrument was featured in an earlier episode and explained pretty much in depth. So I'm not going to repeat all of those explanations, just give a quick rundown of it as it relates to us catching shorted devices. So this has a isolation transformer followed by an auto transformer. And an auto transformer looks a lot like a pot, except that it doesn't have a tapped resistor, but rather a tapped winding, transformer winding. And you can change the AC voltage that's coming by essentially going to one side of the winding and to the tap here, and you will be able to adjust the AC voltage. In this case, the range goes from 0 to 150 in volts. And what that means is if the line voltage here is 17 or 117 volts, I can actually adjust that between 0 and 150 volts. And that should immediately bring up the idea of gently increasing the voltage on an unknown device. It also has an ammeter here. So what you can do is plug the device in here, set the voltage to 0, turn on the device, and then gently increase the voltage while closely watching the ammeter here. And if at any point the ammeter starts exceeding where it should be at, or exceeding the max that you've previously calculated, if you have good reactions, then you will turn back this dial immediately, the voltage will drop to 0, and you just saved the instrument. But if your reaction time is like mine, the instrument will probably go up in smoke if it's shorted before turning this back. So this also has overcurrent protection here, and you just set a value on this dial. The thing is rated at 5 amps, so basically if this is pointing straight up, you just set the overcurrent protection to 2.5 amps. And so if you're too slow to turn this back, this will catch it and turn off power to the device. So let's have a look at that. Turn the power on in here. Now, of course, we already know that that this scope is not shorted. And as much as I'd love to demonstrate it, I'm not going to put a shorting plug in here. I will just show you how this would work. And you go in here and start increasing the voltage. Notice on the left side meter, you can see the voltage come up. And I can now see the power light up on the scope. And we'll just increase it till the analog meter tells us 117 volts, which it is now. Current is very low. The dot's appearing, and we can see the current meter moving up. And what it's telling us, that's using up about half an amp here. Now, if at any point in time, if we saw this thing all of a sudden start moving uncontrollably to the right, most likely the overcurrent protection would have reacted before we could and shut off power. So this is exactly the same principle in saving the scope as a DBT. I can't make a direct comparison because I couldn't find the specs on how quickly the overcurrent protection reacts on here. We know that it takes about 100 milliseconds for a bulb, because that's how long it takes for the filament to light up. And 100 milliseconds compared to the speed of light is a rather large fraction, but it is better than not having it at all. I mean, I'd rather have 100 milliseconds of a shorted device being powered up than having a shorted device that's powered up for a much longer time than that, which is what it would usually take a person to realize it is shorted and turn off power to it. So functionally this would do the same. Obviously this is a bigger device, this is a heavier device, it is a more expensive device, and being bigger, it's going to take up more space on your bench. But it does have a built-in isolation transformer, which is a great safety feature. So I think what the question boils down to then, is it really worth having one of these? And the answer to that is a resounding yes. For just testing, whenever you're working on anything electrical, you should be using this, even if it's only for the fact that it has an isolation transformer in it. But so, what happens to the DBT? Now, opinions differ on which one is better for short detection and which one is more effective at preventing damage from an equipment short. And I'll just add my 5 cents to it. I think that the DBT is excellent for detecting shorts and limiting current to it limiting current to the device very, very quickly. And another thing that this is very good at is, of course, if you are measuring live voltages inside the instrument and you're like me and you either short a terminal strip or even worse than that, you drop a small metallic tool inside it, this will kick in just like it did before because it'll see the short and cut power and reduce damage. Now yes, this does the same thing, but you may notice that I'm not going to have a section on how to build your own because that gets a bit more complicated, expensive, and it's not a realistic thing to build at home. So the final verdict is, in my opinion, is that this is to be used to do a quick check on when you first power up new equipment, and also do a check after you do repairs. If you found something that was shorted and you're working on the power supply or you're swapping tubes or whatever, you should still power it up while it's connected to this to do a short test to see if your repair was effective or not. After that, you should most likely gravitate over towards this guy and have him on all the time because of the isolation transformer in it. Now, one of the shortcomings of this instrument is that are the analog meters. They're not very accurate. I mean, if we look at this right now with the scope warmed up, we got 117 volts and approximately half an amp of current being drawn. So we'd have to put a meter on it and create a spaghetti mess on the workbench, but there is a better way I found, and that was also featured in the original treatment of this, and that is our friend the Kilowatt, which is a home energy monitor, but it does have settings for voltage, amperage, and everything, and it essentially becomes a digital meter. There's also the second one I have, and that one I'll plug in on this side, and if I wanted to measure current, of how much current is exactly being consumed and see it in digital form, I plug the scope into here. So again, you see these aren't doing anything, but that's because they're powered off of this device and the voltage is at 0. So what I'm going to do is increase the voltage, and they're going to kick in at about 50 volts AC. But now what I can do is I can digitally see the voltage and set it to 117. And one thing you will notice very quickly is that the refresh rate of the display is not very high. So if you were staring at these while turning up the voltage to catch a short, it has the same malady with the amperage here. The amperage changes as slowly as the voltage, so catching that manually and turning off the power when you have a short just isn't going to work. But if we look at this, if we remember, and we can kind of see the meter on this side, it's just above half an amp, but this thing tells us that we're at 0.72 amps, so it is showing low. And if we look at the meter from where I stand, it looks like about 120, and this is saying 116.7. So the voltage accuracy of the meter is a little bit better, but the amperage accuracy is not very good. But with that said, you can, with these two guys plugged in, this does become a lot more useful, albeit with a slower update rate. So you don't want to be using it for short detection. For short detection, probably for short detection, you want to leave the kilowatt and the voltage side and see that digitally. But you want to remove this one and actually observe the meter, because you're looking for trends. You're not looking for exact measurements when looking for a short, but rather for the meter starting to deflect rapidly. And it'll work for that in conjunction with the current limiter here. It will do the same job. I call the component in here that lets you adjust the AC voltage an auto transformer. But some of you may not be familiar with that term because it is much more commonly known as a variac. And the variac was actually the brand name of a company that made these things, or made early versions of this, but somehow it's stuck, kind of like Scotch tape. So there's a variac in here, and that's what we affect by turning this dial. So now we have these two devices, and I think I was vague enough about when to use which. This is great for a quick and dirty short test on initial power up of a piece of equipment, as well as after repairs. But for ongoing repairs, you should be using something like this. But since these things cannot be built by yourself and are a little bit harder to come by, this is a nice, inexpensive solution that should be accessible to everybody and should save your equipment should the disaster try to occur. Now, what do we do if we want to be extra safe about shorts? Electrical shorts, that is. We use both of these together. So the DBT is powered by the monitor here, and then we plug in the device under test to the DBT, and now we have both the short circuit protection or the overcurrent protection in here working, as well as the bulb filament working for us, and we have double protection against shorts. And the way that works is, let's make sure this is off. We turn this guy on, and he stabilizes at what, 117.8 or 6 or whatever. And now looking at the bulb as I turn this on, the bulb surges very briefly. Our current reading is very low. I mean, we saw that this meter showed about half an amp for proper operating conditions. We do see the dot or the trace show up, slowly drifting towards the center. The current has increased a little bit, but it's still way off from 0.5 amps, and that's caused because I'm using only a single 100-watt bulb, and it is lit up. Probably again around 10 or 15%. And this current would most likely go up if I brought back the DBT Expander and used 200-volt bulbs. But this should provide us with maximum protection against short-circuit damage. Hope you liked it, and hope you learned a little bit from it, or hope you were able to make sense out of this. And if this was an enjoyable experience, please click the thumbs up button. And if you haven't already, make sure to subscribe, because not only will I be looking at fixing this guy up here, but he has some cohorts which also need fixing. And those are also going to end up on the bench. And I'm pretty sure each one of them is going to be worth an episode and incredibly interesting to watch on how they get fixed. See you later.